Hello?
Yeah. I was unable to find what I needed, but I'll make this work.
Oh, cool.
So the thing is with me when it comes to graphs, because it's like a consistency thing. Like every time I approach a graph, I understand you're supposed to look at the title, the x-axis, the y-axis, like what x is supposed to be dependent and y is supposed to be independent, I believe.
Other way around.
X is supposed to be independent, y is supposed to be dependent.
Yeah, so you,
And
uh-huh.
it just takes me too long when approaching a question and I continuously get it wrong. So now I understand in a way why I got this wrong, but in another way, I'm not understanding like when I'm approaching this question, like how to do it correctly.
Okay. So
Mhm. Can you see the question or is it too small?
I could see it. So you're asking me about this question, right? Because I want to make sure that I do what you want to do, like which is go over like not just the question, but like how to review it.
Yes, like we can go through this one. We can also go through the other one. It's more up, but I just looked at this one this week, so it's more fresh in my mind.
So just like hold that down or rather the one on the bottom. Yeah, you can yeah. All right. Here we go. Okay, so now, well, a couple of things. First, there's so you have to know what um these things are that they're talking about in like in terms of concept. For instance, fluorescence emission, right? And also what happens when an atom can absorb a photon, and what happens when an atom, emits a photon, right? There's a certainly major part of this that is the content of fluorescence that you definitely need to understand what this graph is trying to tell you. Now, the graph tells you, like, let's say, let's try our best and let's see what we can figure out from the graph, if we don't know like the thing about the fluorescence. So it says that figure two illustrates the fluorescence emission spectra for ZPP and PPIX measured from a blood sample. So by the way, so when they say the word emission, what they're talking about is emission of a photon, okay? And if you have an atom here, okay, and let's say that we have an electron in these shells, right? Now, the n is equal to one shell is the ground state. And if the energy between the ground state and the next state, the next shell that moves outward, like let's just say that it's 1 electron volt, okay? So if you shoot a photon at the atom with, let's say, 0.99 electron volts, this actually, so this is why they call it quantum mechanics, because quanta, think about it like quantity, right? It's a specific numerical value that is all or nothing. You can't do it like so basically if you need 1 electron volt for the atom to absorb the photon, 0.99 electron volts isn't going to cut it. Nothing will happen. It won't even get absorbed 99% of the way. Nothing will happen. It's all or nothing. Okay. And if you add more photons, because what they like to ask is something about like, what if you increase the intensity? So
Mhm.
intensity, yeah. So intensity is not, I'm going to write it just, oops. So intensity is not energy, okay? Energy,
Not
you could,
energy into it.
what's up?
We're not putting more energy into it.
Yeah, yeah. So intensity is more so, think about it as the number of photons. Okay. Oh, and then this corresponds to brightness.
Yeah.
Okay. Now, what they like to ask is like, okay, if we shot 10 million of these 0.99 electron volt photons at the atom, would it get absorbed? What do you think?
10 million volts at an atom.
10 trillion, no, oh, sorry. So each photon will still have energy of 0.99 electron volts.
Hmm.
But if you shot like 10 trillion photons at the atom,
Will it still absorb?
yeah. Like what that's what I'm asking. Yep.
Yes.
So remember
To
how
its capacity of 0.99 electron volts.
so imagine that we had 10 trillion of those.
10 trillion of 0.99 electron volts
So 10 trillion of photons,
going to the atom,
each having an energy of 0.99 electron volts.
going to the atom, and would it get absorbed?
Yeah, what do you think?
Yes. I don't think all 10 trillion will be absorbed, but some will.
Well, remember you need to have 1 electron volt of energy, right? So
To
so
get from one to the next.
yes, because basically you have your electron that, so like I could draw like the different shells like this. And let's say we have an electron here in the innermost shell, which is n is equal to 1, right? In order for the electron to get excited up one level or one shell, it needs to absorb an electron, sorry, it needs to absorb a photon which has at least 1 electron volt of energy. Okay.
Okay. So only 1.99 will get through, not all 10 trillion.
No. Um, the photon that I drew here has an energy of 0.99 electron volts. Okay. Now, how much energy do we need for an atom to absorb to absorb a photon?
One.
Okay. Now, do we have that?
No, we have less than one.
Correct. And it doesn't matter if we have one of these photons or 10 trillion of the photons.
Each photon doesn't equal to one, so it wouldn't be able to go.
Yes.
It matters how much the photon
Yeah.
is.
Yeah. Yeah. So now, so now this isn't going to do anything. Now, let's say, so I'm going to use a green one here. This photon actually has 1 electron volt. Okay. Now this one is going to get absorbed, and now the atom has that added energy to it. And like the atom expresses having that extra energy by simply taking its electron and exciting it up one shell. So this electron here will go up and be over here. So if it was here, it'll go up to the n is equal to 2 shell. Okay. And basically, if it relaxes back down to n is equal to 1, it's going to lose that energy by emitting a photon with that same energy. So it's like, let's say you're the atom, and I give you a photon, and you accept that photon, and then you just take inside of like you or whatever. Like imagine you take like a book and you put it up to a higher shelf. And if you bring the book back to the lower shelf, it'll then emit that photon. So it either
Yeah, like shine it out there. I get that already.
Yep. So now fluorescence is a specific instance of this
Of emitting.
of what's up?
It's a specific instance of emission.
Yes. Now that is, let's say that we had a photon that is of a even higher energy level. Let's say it brings it up to n is equal to 3, the third shell outward. So far, we've only been talking about if a photon gets absorbed, an electron gets excited. Okay? And then if an electron gets the opposite of exciting is called relaxing. So if an electron relaxes back, it'll emit a photon. So it's absorbing a photon, exciting an electron, and then it could relax the electron and then emit that photon.
Okay.
Okay. Now I'll go over this fluorescence part really quickly. So basically, if a molecule has a lot of conjugation, in other words, resonance, okay? This is basically like melanin, right? Pigment. That's basically how a pigment like melanin or chlorophyll, or if you just look up like a dye, like they're always going to have a lot of resonance because check this out. What happens with fluorescence is, let's say that, okay, let's just say that the highest energy level that this photon can reach, let's say, is like n is equal to 3, right? But let's say that it's 3 electron volts, okay? So this guy can absorb 3 electron volts, and it'll cause n is equal to 1, n is equal to 2, n is equal to 3. It'll cause it to excite it up to the outermost level shell. But because of resonance, like what does resonance do to a molecule? Does it make it like what does it do?
Stabilize.
Exactly. So now, so far, we've only talked about two possibilities. Either a photon can get absorbed, which would cause an electron to be excited, or an electron can relax, which will cause a photon to be emitted. So far, we've only talked about that. Now, fluorescence happens when the photon gets absorbed, the electron gets excited, but then the electron can relax a little bit, not all the way, but a little bit because of resonance. So let's say it can relax a little bit down from 3 to 2. It can do that without emitting a photon, going from 3 to 2, okay? Because it has resonance. But then when it goes from 2 to 1, it'll be done through the regular way, which means it will emit a photon. But this time, the energy of the photon is less. So let's say like 2 electron volts. So fluorescence is the same thing that we originally talked about with the photons, except the photon that's absorbed has a higher energy than the photon that's emitted.
Yeah, I get that.
Yep. And so that's why like if you have like melanin, it means that we can like absorb UV light, but and that's also why it's called UV vis, in spectroscopy. Like that is used to find double bonds and triple bonds because UV light is high energy light and it can absorb it and dissipate it and emit regular visible light. So I actually don't even need to like really, well, we don't even really need to see this. Well, actually, we do, but meaning the graphs. But you see how the questions are all talking about like photon emissions that are equal, uh,
Mm-hmm.
less energy to excite from the graph,
Mm-hmm.
right? Uh, energy of the photons here. Energy like see how they're talking about the energy of the photon during
Mm-hmm.
excitation, right, is greater than the energy change of the resulting electronic transition in the molecule. So basically, like I think you probably like saw the graph and you totally understood that yes, x is the x-axis is wavelength, y-axis is oh intensity. Good thing that we went over that because now we're talking about brightness, number of photons, right? But the wavelength part is going to tell us more about the energy because energy and wavelength are inversely proportional, right? So as we move to the right, the energy goes down, right? Because of that,
Mm-hmm.
the inverse relationship between energy and wavelength. So now if we look at this, okay, so now they're saying that ZPP is excited at 425 nanometers and PPIX is excited at 407. Okay, that means that this guy, smaller wavelength means higher energy, right?
Yes.
So this guy here, we don't even really need the graph that much. I mean, like, we need it to compare these two, but we could see that, okay, one of them um has a smaller wavelength than the other one, and the one that has a smaller uh wavelength, let me see here. Okay, hold on. So in the graph, the ZPP is the like black line, and okay, so we are gonna have to do some graph stuff here. So we see that there's this value and this value for the ZPP. And then for PPIX, we have the gray values here. So now, um, okay, I guess it's starting to make sense now. So since we're talking about the fluorescence emission spectra, we're gonna have um, the graph showing us the emission of the fluorescence, but what they're talking about in the description here is the excitation part. So, when it comes to excitation, PPIX has or requires more energy, right?
Yeah, because it's more photons are absorbed and less are emitted.
Wait, remember? Oh, you're talking about intensity or energy?
Energy, because it will be higher energy with the photons absorbed.
Yep. Mm-hmm.
And it has higher it has higher photons being absorbed, which is 425.
When you say higher, tell me again what you mean.
Like the 425, that's the photons that's excited at 425.
Uh-huh.
That's higher than VIX. That's excited. This is electrons emitted.
Hmm. So I think it would be good to actually talk about because each of these choices are talking about possibly four different things, right? So first, we need to see that for the ZPP, if it's excited at 425, the graph shows that it is emitting at 595. So I guess I'll just write that like, I'll just write it in red over here. So for ZPP, I'll write like, okay, excited here and then emitted here. So for ZPP, it's excited at 425 nanometers. For the PPIX, it is excited at 407 nanometers. And they're telling me in the question stem that the peak, or sorry, the highest intensity fluorescent peak in figure 2, that is showing us, so for ZPP, the emission, the fluorescence emission is 595 nanometers. And then for the PPIX, it's 625 nanometers. So if I were to order like rank these all, you know, in order, or I guess we could just compare them directly. So if we look at choice A, they say that ZPP and PPIX have peak photon. Oh, okay, this is going to be a good exercise. So I'm going to go through these and you can tell me like which values we can use in this kind of like, I guess, table that I wrote up here. So ZPP and PPIX have peak photon emissions. So what are we going to look at?
Photons?
So from here, so for instance, the 425 is the excitation wavelength for ZPP.
Yeah. You're asking like which side column to use? Or
Yeah, yeah. So this could be a good way of like killing two birds with one stone because this way you can tell me what these correspond to, and then you can see the difference between the excitation and the emission.
okay.
Mhm.
So A would be what? The emission side?
So so like what would be the energy of the photon emission for ZPP, like in terms of wavelength over here?
Like it says 595, but it wouldn't be equal to PPIX because that's a 625.
Yep. All right. Good. 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 Let's get B
Trying
for
to
now.
figure out what you're talking about.
Let's try C.
Okay. The energy of the photon used to excite
Mhm.
CPP is less than the energy of the photons emitted by the molecule during fluorescence. So the ZPP excited is 425, but the emission is 595, which is less.
So C can't be true, right? So the energy to excite ZPP. So and so by the way, these are wavelength values and they are inversely proportional to the energy. So higher energy, smaller wavelength. Yeah.
Okay, so yeah, that's not true.
Uh-huh. Correct. And now, in addition to that, this can never be true because fluorescence always.
Has to be like less than what is absorbed so you can
Yes.
know how to excite it. So
Very.
like in a sense of concept like that, yes, I get it. But I don't like when I'm faced with a graph
Hmm.
and the numbers and then we're all thrown off altogether when I get that part of the concept. Like of course I need more to absorb and I'm going to excite or like emit less out.
Got it. Got it.
So like that's just basic.
Hmm.
Like, yeah, we get that. But okay.
Yep. So yeah. So in the graph here, so they like just from the graph alone, we do need the info that they have in like the description here, right? And so they're telling us that ZPP gets excited at 425, and we don't see any peaks that are at 425, but that makes sense because this is showing us the fluorescence emission spectra, right? So
Mm-hmm.
we're not going to see a 425 or a 407, but they're telling us that these peaks correspond to the uh highest and like I guess like there's two possibilities for fluorescence peaks here. And in this question, they're just telling us essentially to look at the highest intensity peaks. So we're comparing it to that one, these two, just for this question. But but yeah, you definitely will need like this and this context to make sense of why we have two peaks. Because it could be confusing. It's like, okay, they're telling us that they're excited at these wavelengths. They're showing me these other wavelengths. Why don't I see the 425 or the 407 in the graph? That can be pretty annoying, but yeah, now that you understand like the fluorescence concept, it should make the graph a little bit more hopefully make sense. Um
So you want to do D?
what's up? Oh
You
yeah.
want to do D? The energy of the photon absorbed by ZPP during excitation is greater than the energy change of resulting electronic transitions in the molecule. What? I don't think that has anything to do with electronic transitions.
So so okay, I guess what I was focusing on here was the difference between excitation and emission.
Uh-huh.
But the stuff that I drew like this and this,
Mm-hmm.
that's
That's the transition.
correct. Yeah.
So if that is into saying that because the energy is in ZPP is higher, like its excitation energy is higher than the energy it takes to transition from one location to the next.
Yeah. So this is so this is from UWorld, is it?
Yeah.
Okay, okay. Yeah, they can be a little tough. So this is actually asking us a little bit more. So this is just saying that so our answer to this is the reason why, for instance, ZPP, just to use an example, it could work for any example. Like, why does it get excited at 425 nanometers? And the reason is between the like ground state, the n is equal to one shell where the electron naturally hangs out, and the next energy level is equal to that energy change that you need. It's like up here, remember when I said that the energy difference between n is equal to 1 and n is equal to 2 is 1 electron volt? That's
Hmm.
why the one elect you need at least that 1 electron volt for that atom to absorb it, because 0.99 isn't enough to cause that electronic transition.
Okay.
Mhm.
And ZPB requires less energy, which means more photons, a higher wavelength to excite its electrons from the ground state than does PPIX. Yes, it requires more of the wavelength, less of the energy to excite it from the ground. Yes, because one is 425 and one is 407.
Yeah. So that ground state is the n is equal to 1 shell.
Mm-hmm.
And that is when they say excited, like that's the first thing because it starts off at the ground state. So they're talking about the excitation. Yep.
All right.
So yeah, this is a really high yield. So it's good that we covered the stuff about photons. You will always see stuff about photons. And like also anytime you see them give you like 400 nanometers and stuff, like a wavelength, know that if you had to, you can determine its energy and its frequency, because of the energy of a photon is Planck's constant times frequency, or Planck's constant times the speed of light over wavelength. So just anytime, so like that means like if they all we have, like if they give us anything like 400 nanometers, if we needed to, we can basically figure out like everything about that photon. Okay.
Okay.
Mhm.
Um, I just wanted to look at like how I reviewed this question real quick,
Yeah.
and then after that, I guess we'll go over the Altius. I guess the next time we meet, can we go through how I approach questions?
Yeah, absolutely.
Because I don't think we have time for that. So
I Yeah, okay.
can't stand it when it starts glitching.
Mm.
So with this one, we'll just keep the same question. I put the question here, I got it wrong. So I was like, high intensity graph dictates. Like I reword the question because my problem is with AAMC is that even though the question is right in front of me and I'm reading it, I don't know what it's asking me.
So
Like the buzzword or
mhm.
whatever, what have you. So I put the question like what I think it is right there. Then
Which like
which
what's
question best for? The one we just went over. Which I don't know where that graph is. You need to see that question again?
uh wait, um the one that we just went over, the photons?
Yes.
Um like I see like you Cl to OH and
No, not right here. Right here. I'm sorry. It's glitching back. Let me turn my camera off.
is so the question is what the high intensity fluorescence graph dictates?
Yes. That's what I believe the question to be asking from the question we just went over.
Oh, I mean, that's kind of, I mean, it just shows that, uh,
And then so basically, I would write the question, then I'd write the answer that it has, like with a little explanation. And then sometimes I'd be lacking in like understanding of like concepts. So I'd be like, energy of a photon is inversely proportional to the energy of a wavelength.
well,
And
So energy, so wavelength is distinct from energy. Like you can't like energy of a so energy of a photon, you can equate that to Planck's constant times frequency or Planck's constant times the speed of light over wavelength. So they're all distinct things, right?
Hmm.
So the energy of a photon you could write is inversely proportional to the wavelength, but it can't be the energy of a wavelength. You know what I mean?
Yeah. Okay.
Um, but uh, but okay, from that graph that we saw, like that's pretty much, the one
It.
it's like wavelength. So like what about that? Like,
What's the question?
oh, I'm just trying to ask like what like because we went over that graph, right? So I just want to know what you're at.
I'm telling you, this is how I review my questions after I'm done. And I need to know, like, am I wasting my time taking my time to review it like this? Because I've discussed with you last time that it's taking me a while to review it. So then
Uh-huh.
to turn around to go answer questions after I've done reviewed questions, like, I need to know, like, should I find a different way to review? Like, what do you suggest?
Well, so I think that the issue with that, like the question that we just went over, was it was predominantly content because the graph itself is just showing you that there on the x-axis is your range of wavelengths. The y-axis is intensity, which means number of photons, not the energy of photons, but number. And in connection with everything else that they're saying. Like the graph itself isn't really telling you much. It's telling you that there's two molecules that exhibit fluorescence and they have distinct peaks, like at specific wavelengths. There's distinct uh and if the y-axis is intensity, the peaks are where there's the highest intensity, right? So like I could even like draw like one like an example like so let's say that we have here, let's say this is so this is the same so this is fluorescence intensity here, the same as that other graph. And then the x-axis is just your wavelength, and we have two different peaks. Now, which of these peaks would be an example of and let's say that this is a molecule that's exhibiting fluorescence. So which of these peaks is the fluorescence emission peak?
Would it be the one that's 520,
Got it.
the lower one? I get that. It's not about the graph specifically. It's about the time I'm taking to review each question, like every other question.
Yeah. So with that, it really just it's
Depends on me.
uh just at least from what I've seen, it's more of a uh content thing
Hmm.
for this. Like so if you have
Content thing.
uh you know like the or wait, this copy of is this from like what I made?
Yeah, this one is from yours that I
Yeah.
copied over
So
here.
yeah, click that and yeah, do like a control F.
Control what?
Control F or
Oh,
Mac, like whatever that is.
hmm.
Yeah. Type in like yeah, fluorescence. It starts with a U, like it's FLU. It's weird. Okay. Yep. Sorry. Maybe I was wrong. Uh
Mm-mm. How do we spell fluorescent?
um
But I get what you're trying to say, like highlight them and review them over or something.
Oh wait, this is
Chemistry,
oh
CP.
um sorry, okay, type in, I guess type in photon. Okay. So okay, so we have classification of electromagnetic spectrum, photon energy. Let's scroll down some more. Yeah, all of this stuff. Conjugated systems, electronic transitions, right? Um,
Yeah, I need help with all of these. These are always problems.
yeah. Electromagnetic,
Go down.
ultraviolet, conjugated systems. Yeah. So I don't know why, yeah. But yeah, this should depict for you the, let me see if I can find like a, so basically, like, yeah, so when you see like stuff that they're talking about, that, yeah, this is probably going to be like close to it, but like for the most part, like, uh you know, the stuff about light and how it's electromagnetic radiation, how there's, photons like getting absorbed and causing emission and things like that. That's stuff that you can use like this to see, like, okay, what is like officially from the MCAT, what do I need to know about this? Uh
Mm,
and then you can, and UWorld is really good because like for that question, they probably have really great explanation for, or like a, like a solution that explains like the concepts and stuff. Like, is that something
mhm.
that you saw?
Yeah, that's what I would write down, like as extra notes and stuff
Yeah.
when reviewing.
Yeah. So I could, let's see. So yeah, so when it comes to reviewing the questions that you're getting wrong, that's what I would do. I would see like, okay, this is like so for that question that we just went over, that, it, sure, it's one question, but it involves like so many other different types of topics that are extremely high yield, that you should, like, you can't, like, you must know that stuff. You could actually, so like if you give me, like, I don't know, I think you, I'm not sure if you gave me access to this or not, but when you like write it out and stuff, I could, like, take a look at it and like look at, like, okay, is this like super high yield? If it's like not super high yield, um
Yeah, I title it so like you will be able to like see what topic is being like looked at with you world. Like for instance, this one actually popped up under periodic trends,
hmm
actually. So I was just doing periodic trends,
hmm
which I was getting wrong most of it. Like I probably got like a low, like 11 right or something.
uh
And the top it says enogen. So like it'll tell you.
Got it. Yeah.
So I've been trying to do it this way. So hopefully it's all right.
Yeah. So that,
It
so
just takes time.
yeah. So I could always take a look at these, and I can just like, we could even like probably do it like now. Like I could take a look at these and I'll be like, okay, like this is like, we have to know this. This is like something that we can like prioritize to be like less so. Like toscillates and stuff is not going to be as big, but like, um, but yeah, you can kind of like scroll through these. I can, oh, and then like that thing SN1, SN2, like I have a PDF that goes over that as well. Um,
Okay, great. Because I was trying to figure out like what is like the easiest way to identify what is SN1, SN2.
yep,
And I
yep.
was like, it's usually tertiary, two-step. Like I answered that question myself. This one I have highlighted. We talked about chalcone substituents and
Yeah.
percent inhibition.
So let me just make sure that I got this. Um,
Stop sharing. Hold on.
I got a unknown buzzwords thing and
You have a list? Because I started doing my list for biochem.
um palette like a bunch of stuff like that. So yeah, I have that document and
Do you have a, I have so many of them, but do you have a,
I think I found it. And this is under which tab was it? CPQ. Yeah,
yeah, CPQ
I got
review?
it. Okay, cool. So do you want me to start from the top or where should
No, we don't have to go through all of them. Oh my goodness.
I
You
start?
said you found the SN1, SN2 one, so that works. And Joe said that I should just put them in like a AI and it'll make flashcards for me. So we don't have to go through all of them. I just wanted to know that the way I was doing it was correctly,
Oh
you
yeah,
know,
I was just gonna go through them and like highlight the ones that like I like
needs to be okay. All right, we can do that.
stuff. But check out the drive link that I put in the full like I'm pretty sure I shared this with you also, but
Yeah,
um
you did share one thing with me. What had my name on it?
oh yeah, so there's that, and then this is a shared Google Drive that has lots of like really good stuff in it. So yeah, try that link out, and in the PDFs folder, there's a document called Organic Chem Intro. So take a
Hmm.
look at that, and while you do that, I'm gonna like look through these and kind of like I'm gonna go into like suggestion mode, and I'm gonna just talk or write out like the. Okay, so
Is it a phone?
what's up?
Trying to figure out which PDF it would be named as.
Oh yeah, it'll be called Organic Chem Intro in the PDFs folder.
Okay.
Oh, and here's another resource I'm putting in the chat that could also be useful for Orgo, but look at the PDF first though.
I'm still looking for it.
What's up?
I'm here on the drive under my name, and it's not in the first few of them. And I don't see a
So,
PDF folder. I see notes, biochem, additional notes, OpenStack.
what? Sorry, what do you think?
I'm looking at, I'll just actually share the screen. Nope, it was on the-
Oh, so it's going to be something just in the search bar. Uh, type in Shane MCAT.
You said what?
Just type in my name. Shane.
Oh, okay.
Okay. Hold on, maybe.
This is the only thing that you showed me that Excel sheet.
Okay, hold on. Let me see. I show this. Okay. I sent it to both of your emails. You should get something there.
Got it. The whole folder.
All right, yeah. So there's a
PDS, got it.
all right, and I went through the that thing and I put like in green the ones that are high yield that you need to know. So most of these are like physics concepts, like for instance, like resistance, photons. Oh yeah, you could even do some of these now probably. Like what happens to the frequency and energy when a photon goes from red to green? Um, so
Um, it's red to green, so that means it's increasing away. No, it's something about its energy, like it decreases by going from red to green or something. Am I saying that
yeah,
right?
you're on the right track. Um So the visible light spectrum is going to be going, it's going to like be like in order of like Roy G. Biv, but
Mm-hmm.
that's in order of decreasing wavelength and increasing.
Increasing energy. This
Right.
is inversely related.
Yeah, yeah. And you can even think about it like, infrared. Infra, the word infra, the prefix means less than. So infrared is less energy than red. And then you have Roy G. Biv. And then where you have the violet. Ultra means more. So ultraviolet comes right after that. And as you get like to ultraviolet and, smaller wavelengths, higher energy, like that's where it gets more and more dangerous. But but yeah, these things that I put in green are larger top like subjects that fall under. Oh yeah, you have them down over here under content. So like circuit, electromagnetic spectrum, right?
Mm-hmm.
Electrostatics, more circuits, wavelength. We have electric force, metal conductivity, electric field lines, magnetic field, Lorentz force, resistors. We could probably I don't know, the next time we meet or something like so I would say like yes, to focus on the ones that
You
like
highlighted.
yeah, because those
Got it.
yeah. And then, we can meet at some point and go over it because like I can go over these pretty quickly with you, but yeah, I would focus on those. Um
Okay.
yeah.
I'll just have like an AI flashcards for him to work on them because I think it can make like MCAT questions or something.
Yeah. Just the thing is with like the flashcards, like that can help you like retain the information, but you want to really under
Apply it. Like,
yeah,
yeah.
yeah. Like for instance, see how what I can say. So so if I take off my glasses, the energy, so these like they're blocking out blue light. Like lots of glasses block out blue light, but mine also like are tinted red. So does that mean that the blue light photons, when they go through glasses, like what happens? Do they like just turn into red when they hit my eyes? Like what do you think?
So you're saying when you take off your glasses, I gotta look at you for this one. You said when you take off your glasses, the infrared, what?
Sorry. So basically, like, you know how there's blue light blocking glasses?
Mm-hmm.
Okay. Now, ironically, right? Have you heard of seasonal affective disorder?
No.
So basically, it's like when people like let's say who are from California or something and they go live in England. Uh, this is like for like hundreds of years or whatever, right? They get depressed, right? And why do you think they get depressed?
Because the season is changing, so like their energy is kind of like low and
Yeah,
different because of the outside like energy and
yeah,
stuff like
because
that.
I don't know, like England, it's like always like
Dark and
overcast.
gloomy and
Yeah,
rainy.
yeah. So something that they would so basically like that actually causes like a measurable change in the serotonin that's produced because when blue photons, right? When they hit our eye, like meaning, they go through our eye and then they hit our retina, it our retina and the optic nerve and all that stuff that it's connected to recognizes the color based on that energy. If it's a high energy, right? Like relatively speaking, right? Higher
Mhm.
energy is going to be like if it's a blue light or something like that. Lower energy is going to be for like more reddish light and stuff like that. And the blue light causes you to make more serotonin, which improves your mood. Which is why for people who would have seasonal affective disorder, they would part of their therapy would be like they would have to look at like kind of stare at uh like a blue lamp, high brightness blue lamp.
I have one
Oh yeah.
because it's an outdoor. It's like an outdoor light because you're inside so much. Yeah, I have.
Yeah. Yeah. Because that's mimicking the light that we get from the sun, right? Now the thing is that serotonin, even though it makes you feel happy and stuff, like it elevates your mood, it also promotes wakefulness, which is why over the course of a day, we're still being from our computer screens, we still have blue light hitting our eyeballs and going to our retina and then transmitting that signal. So it can make it hard for people to fall asleep. It could also lead to strain because think about it, it's high energy uh, photons, really like relatively high energy photons. There's also a program or something called Flux, if you ever wanted to look that up. It automatically based on your like uh I guess like latitude, like your location, automatically like over the course of a day lowers the amount of blue light and makes it more red light.
Mm-hmm.
So,
Lord, I
uh,
love the Lord.
yeah, like light, like the colors of light actually like it's not like okay, they're all equal and they're all just a different color. It's like each color has its own energy, like literally. So yeah. So I would say
Mhm.
to review the like for instance, like,
The Gen Chem notes. So I'm gonna definitely review that because I'm
yeah,
looking at them now and they look really good.
yeah. And then like proton versus electron, definitely need to know that. The stuff with like the circuits and voltage stuff, like we can that stuff could be that could be kind of difficult to learn on your own. So like, we can probably like do more of that like when we meet
Next time.
stuff. But on your own, definitely like maybe I'll do like even like another like layer of green. Oh, that's some ugly color. Um like maybe I should do yellow. I don't know. So like um maybe I'll just do like orange to be like, okay, like even like start here, maybe something like that. Um, oh yeah, orthos. Yeah, okay. So I think I remember this question. This question here is like we're gonna have to go over the concept first, the Coulomb's law, but this question with the sphere is like one of the most perfect kind of like MCAT, like what they like to ask you and
Hey, hey,
stuff.
my review notes are actually looking like something.
Yeah,
Yay.
the things like the thing with like the magistral versus magistral acetate and stuff like that, like I think that second resource, the MCAT Organic Chem, the link mcatreview.com .org, um that one goes over like that stuff really in also like a very concise manner. Um and yeah, so I would say basically that um that look at the stuff that, I highlighted in like the whatever green or like I don't even know, like the orangey color, and then
Mhm,
look at the content part on the left, like electromagnetic spectrum. That's a great place to start.
mhm.
Then you can use the CP content thing here, and then you can type in like electromagnetic spectrum and like go over like each of those topics and then use the drop down menu to adjust your level of understanding.
All right, sounds good.
All right. Awesome. Awesome. And then yeah, so try that out the best you can. And um and yeah, I think that will be an efficient way of going over this stuff. Okay.
All right. And then do you want to go over Altius?
Oh, I
Because
can't.
you want me to take an exam this Saturday?
Oh. So I mean, I can't write now because we are
Or
like
done? It's 9:15.
time, but I mean, is are you available to meet at like any other time this week?
No, because I'm planning a health fair
Mm-hmm.
and I'm booked.
Got it, got it. Okay, and you're taking that test on Saturday the 24th?
Yeah, I'll take it on Saturday.
Okay,
It's either I take it on Saturday or I take it on Friday.
got it. Yeah, and like even, like even so, like I still think like the stuff that we like that I like highlighted and stuff in this document, like it's still going to be like really high yield stuff that you have to like pretty much like, learn anyway. So I think that way we can kind of even get more done. Because it'll probably take a while to like, cover like electromagnetic spectrum, all that stuff with light and photons and things like that.
Hmm.
And the stuff with circuits and things like that, and the Gen Chem stuff. Noble gases least reactive, the halogen halides and stuff. So, um, yeah, like and like feel free to like send me emails and stuff. I'll try to like help like do like help you out as much as I can, like in between that and your test.
Okay. And then Altius is very simple to get in and all that kind of stuff because I didn't even look at the pricing.
Got it. So let me pull up your thing where we talked about May 24th. Yeah, so with the Altius, you I don't know if we talked about this part, but you're not going to be doing the Altius cars section.
No, we did not talk about this.
Okay. good. So basically what you're gonna do is let me share my screen here. So I'll even write so like it's like step one, like Altius CP section. Number two, Jack Weston cars exam three. B back to Altius basically. And back, still with Altia. So basically what you're gonna do is once you get up to what is it? You're gonna do your Altia CP section like you're supposed to, like timed and everything. When you're done with that, open up another tab, or you could even have it ready on the left. So go to jackweston.com. On the left here under practice exams, click that. You're going to get a bunch of these full length ones. Don't worry about those right now. And then the cars practice exams, Los Angeles and Chicago. Don't worry about these. Okay. So that's what you're going to do. So you're going to start with Altius, right? Doing everything timed and, normal. Do your CP section. When you're finished with the CP section, you then go to a different tab, open up Jack Weston, and again, you go to the left here where it says practice exams, and then here it says Los Angeles.
Mhm.
Go to exam. It'll be like a full, exam. Obviously put in like the correct time, that it takes and everything like that. But you do that exam, the cars one, and when you're finished with that, go back to the tab with Altius and just finish up where you left off. Obviously, skip the cars, but do the BB timed and then the Psych Soc timed. Then at the end, you'll get a score for each of the sections, and we're just gonna input the Jack Weston car score uh, for the Altius car score. But basically, you're going to be doing your Altius tests, but you're only going to be using for the cars Jack Weston cars. Okay.
Okay, sounds good.
All right. So awesome. 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 I hope this was helpful and good luck on your practice test. Okay.
Okay, thank you.
All right. Take care. Have a good one.